Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Decision-Making Artificial Intelligence, Homeland Security, Defending Critical Infrastructure. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Homeland Security. Case: Defending Critical Infrastructure. Sun Tzu, in the book The Art of War said, "Every battle is won before it is fought." In the war on terror, planning supported by the scientific method can avoid conflicts, so that many battles are won without a fight. For disasters caused by the humans it implies. The overall objective is to minimize the potential economic and human loss, and the social impact of the terrorist attack. To do this, models are proposed that study the opponent and hypothesize the decisions that can be made, using game theory models, on where, when and how to allocate defense resources. The state-of-the-art of scientific planning of confrontations, attackers versus defenders, is the use of competitive game concepts developed by John Nash. Security games study the convergence property to the equilibrium of a sequence two-player dynamic games, played by an attacker and a defender. The fundamental features of the game are: the evolution of the game is based on a stochastic fictitious play process. Players do not have access to each other's payoff matrix, and each must observe the other's actions up to present, and plays the action based on the best response to these observations. When the game is played over a communication network, there are another practical issues that need to be considered. Network latency. The players may make random decision errors from time to time. The players' observations of each other's previous actions may be incorrect, and the players will try to compensate for these errors based on the information they have. Adversarial risk analysis, ARA, is a relatively new area of research that informs decision-making when facing intelligent opponents and uncertain outcomes. It enables an analyst to express her Bayesian beliefs about an opponent's utilities, capabilities, probabilities, and the type of strategic calculation that the opponent is using. Within that framework, the analyst then solves the problem from the perspective of the opponent, while placing subjective probability distributions on all unknown quantities. This produces a distribution over the actions of the opponent that permits the analyst to maximize his expected utility. ARA is a decision-theoretic alternative to classical game theory, GT, that uses Bayesian subjective distributions to model the goals, resources, beliefs, and reasoning of the opponent. GT generally assumes that all participants in the game have the same beliefs about the other players, and that all players know those beliefs are known. This common knowledge assumption is frequently unrealistic. The ARA divides uncertainty into three components. Random is the uncertainty in the outcome conditioned by the choices of the opponent. This is managed through statistical risk analysis. Epistemic, a competitor does not know the opponent's utility function, nor the evaluation of the probability of outcomes, conditioned on decisions, nor even his resources, but a Bayesian competitor must be comfortable making subjective probability evaluations on each of these quantities, and conceptual, it reflects the fact that the competitor doesn't know how his opponent makes his decision. Maybe that the opponent is a game theorist, and looks for an equilibrium solution, or that randomizes, or follows some other protocol. ARA can lead to mathematical formulations whose complexity is comparable to that found in GT. There is no easy way to reason about other people's strategic thinking in realistic situations. Nonetheless, the decision-theoretic approach sidesteps some of the common criticisms of game theory. Important ARA applications are in defense, counterterrorism, corporate competition, criminal gang movements, homeland security, and cybersecurity, risk analysis. In 2002, the USA Department of Homeland Security deems 13 infrastructure sectors that must be protected: agriculture, banking and finance, chemical industry, defense industrial base, emergency services, energy, food, government, information and telecommunications, postal and shipping, public health, transportation, and water. Attacker and defender models. The core of an attacker-defender model is an optimization model of an infrastructure system whose objective represents the system's value or cost to the defender, our society, while it operates. For instance, the maximum throughput of a pipeline network could measure that system's value, while power generation costs, plus economic losses resulting from unmet demand, could measure the cost of operating an electric power grid. Attacker-defender model. It is assumed that the defender operates a system to minimize cost, which is represented by an objective function. The defender is a misnomer in these models, because the models do not directly represent defensive actions. Call it system operator would be more accurate, but awkward. The model posits that an attacker wishes to maximize the worst damage he can cause, by restricting the defender's operational activities. The attacker determines an attack plan, AP, in which he specifies which assets of the defender he will attack. Attacking an asset prevents the defender from carrying out activities that depend directly on that asset. To determine the set of activities included in the AP, the attacker solves the optimization problem, AD, that is a type of B-level program. A B-level program is a type of Stackelberg game. Here, the terms leader and follower in a Stackelberg game represent our attacker and defender, respectively. Defender-attacker-defender model. The solution of an AD model identifies the most critical set of assets for a system. To approximate the solution to the optimal defense problem, for example, to identify a near-optimal defense plan, given a limited defense budget, it is possible to solve a defender-attacker DA model considering the solution to the AD model. But how do we identify the truly optimal solutions? In theory, we simply embed the two-level AD model into a three-level defender-attacker-defender DAD model, which corresponds to a bi-level problem with a lower, internal, level that corresponds to the AD model with a restricted set of attack strategies. Therefore, the defender wants to identify an optimal defense plan so that when the attacker resolves AD, the benefit that the attacker perceives, i.e., the worst damage that the attacker can inflict, is minimized. Homeland Security. Case: Defending Critical Infrastructure. This section is based on the paper Defending Critical Infrastructure. The vulnerabilities of a space-sprawling supply chain are growing and riskier. Human intuition is incapable of optimally dealing with all the attacks that such infrastructure may suffer in physical space, or in cyberspace. Decision-making artificial intelligence provides the right tools to maximize the success of those who must defend society. Critical infrastructure protection. Development of tools to anticipate, identify, and measure the risks to which a nation or region's critical infrastructure is exposed. This is to reduce the risks and consequences of an attack. B-level and tri-level optimization models to make critical infrastructure more resilient against terrorist attacks are used. Each model features an intelligent attacker, terrorists, and a defender, us, information transparency, and sequential actions by attacker and defender. 3 real examples are presented. The U.S. Strategic Petroleum Reserve, the U.S. Border Patrol at Yuma, Arizona, and an electrical transmission system. Each exercise gathers open-source data on a real-world infrastructure system, develops an appropriate B-level or tri-level model, and uses these to identify vulnerabilities in the system, or to plan an optimal defense. Only the first case is discussed in this presentation. The U.S. Strategic Petroleum Reserve. Attacker-defender model. The case seeks a defensive plan for the SPR that lies in Louisiana. Figure depicts that section as a network, showing the Bayou Choctaw and West Hackberry storage sites as source nodes for refineries, 4 ports, and 14 export pipelines as sink nodes, several pumping stations and junctions as transshipment nodes, and several pipeline sections connecting the nodes as network arcs. For 3 defensive options, optimal attack plans were evaluated assuming that the attacker can destroy any network components. Below are the defense options and results. Baseline: no defense. Destroying only 2 components of the system, the sources, reduces the optimal performance of the system to 0, i.e., it leads to the most expensive possible system operation. Therefore, a sensible defensive plan must include the sources. Protect critical core components. Uncover a critical backbone of components that, if protected, ensures the connection of the two sources to many, usually redundant, parts of the distribution network. With the backbone defended, at least 7 undefended components must be destroyed before the system's maximum output drops below half. Protect a 10-mile radius safety zone around each source. This protects 3/4 of the system's capacity for any conceivable number of attacks. The decision depends on an analysis of assumed cost versus protected capacity, which must be performed by the decision maker. Border Patrol, Defender-Attacker Model. In particular, the model wants to improve the likelihood that border defenses will detect a foreigner, who may be a terrorist, trying to infiltrate the country. For simplicity's sake, it is assumed that a single infiltrator will choose from a set of known routes to attempt to enter the U.S. illegally. The figure shows a map of the Yuma border area, along with a skeleton of the infiltration network, that describes the routes an infiltrator might take from Mexico into the U.S. through conventional portals, or through road or trail raids. The intent is to spend a limited security budget on procedural changes, sensors, highway patrols, and helicopter patrols, to increase the odds of detection at individual arcs and thus maximize the likelihood of overall detection. Options for procedural changes include closure of certain legal portals, and use of sensors, or helicopter patrols, for the detection and signaling of ground units. Ground units are vehicles and crews that follow signals from helicopter patrols. It was to study 4 scenarios. The results are specified in terms of probability of detection. Baseline: no security improvements. An infiltrator would cross the border and traverse downtown Yuma, exiting the city to the northeast. Probability of detection equals 0.04. 1 checkpoint, 1 remote observation post, 2 road patrols, sensors to cover at most 15 road segments, and 1 helicopter, all visible to the infiltrator. Probability of detection equals 0.07. 2 checkpoints, 1 remote observation post, 2 road patrols, sensors to cover at most 15 road segments, and 1 helicopter, all visible to the infiltrator. Probability of detection equals 0.11. Surprise interdiction of downtown Yuma infiltration route. 1 hidden sensor field, and 2 surprise roadblocks are located optimally. The probability of detection rises to 0.60 because information has been hidden from the infiltrator. This represents an interesting use of a Stackelberg game in which we fool the follower, infiltrator or attacker, into playing one game but evaluate success according to another that is more advantageous to the defender. This game will be played many times, however, the infiltrator will eventually catch on to the ruse. 2-person zero-sum game theory may be needed here. Electric power grids, Defender-Attacker-Defender model. It was developed a decision support system called the Vulnerability of Electric Grids Analyzer, VEGA, that uses an AD model to identify critical components in a power grid. Criticality of grid components is measured through disruption, which may be viewed as the penalty for unserved demand, weighted by different customer sectors. The models assumes that a group of terrorists, using limited offensive resources, will attack and destroy grid components to maximize disruption. In VEGA, a standard optimal DC power flow model is used to simulate the electrical grid. This LP approximates the true, nonlinear AC model, but the industry deems it adequate for security analyses. In fact, an independent system operator may solve a model like this thousands of times per day to ensure that a power grid maintains N-1 security standard that can still meet all customer demand after any single component failure. In this case, the sub-models represent different system states as demand varies and repairs proceed, over time, after an attack. The results presented in the article show that an intuitive defender plan yields a cost almost 28% higher than optimal. This percentage would likely be even higher in the real world. Presumably, a planner who suboptimally forces defense will not optimally allocate his remaining defensive resources, either. Lessons learned. The RAND Group, led by Gerald Brown, concludes. The answers are not obvious. The most damaging coordinated attacks, and the most effective defenses, can be unintuitive. This public infrastructure is huge and complex. The analysis of such a large infrastructure deserves rigorous, optimizing, and decision support tools, to formalize the notion of a transparent, two-sided conflict. High-fidelity models are achievable. We can formulate, find data for, and quickly solve high-fidelity models of critical infrastructure systems. Simpler, aggregated models may appeal, but unless verified by high-fidelity models, their answers will always be suspect, and insights may be lost. Heuristics and rules of thumb are useful, but not for identifying vulnerability. A reasonable heuristic for identifying good sets of defensive actions leads to sensible defensive plans, only if the system is very simple, or if the attacker is naive. If we base defensive measures on heuristically identified near-optimal attacks, we run the risk of being attacked by an aggressor who is smarter than us and our heuristics. Reliability is not the answer. We need to protect groups of critical components in our infrastructure systems, rather than backing up less reliable components. Malicious and coordinated attacks can be more damaging than random acts of nature. The attacker has the advantage. This is the opposite of classical military theory, and occurs, in part, because of the asymmetrical nature of this conflict. The defender must protect a huge, dispersed set of targets, while the attacker only needs to concentrate on a small set of chosen targets, to maximize damage. The data is available to everyone. The attacker also has an advantage in terms of information. Government agencies have created websites that offer a lot of useful information, to both citizens and terrorists. There must be an appropriate balance between the public's right to know, and the publicity of our vulnerabilities. Some systems are naturally robust, while others are not. Our road networks should be remarkably robust, fuel piping and storage systems are very fragile, most other systems are somewhere in the middle. Protecting infrastructure from attacks can be costly. However, by understanding the nature of the most damaging attacks, we can improve the robustness of a system for a given budget. Critical infrastructure has been built to be cost-effective, without worrying about belligerent attacks. There is a lack of economic incentives to mitigate this situation. An adequate level of redundancy and/or reorganization could be economical. Some types of infrastructure, for example, supply chains, will benefit, at low cost, by adding some alternative shipping routes, or by wisely relocating acceleration capacity. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.